Hey, hello and welcome back everyone. Moving on to section 3.2, we're going to be discussing multidimensional optimization, and in particular, the method of Lagrange multipliers is going to be one of our favorite methods to optimize multidimensional functions. This is going to be somewhat similar to the cases of optimization you probably studied in Calculus 1, so I kind of want to remind everyone what that looks like because very analogous operations are performed in higher dimensions. It's just that we have a little bit more to keep track of. And so in Calculus 1, let's think about how we would optimize a function. So if we had a function that was defined over a closed domain, and really this needs to be a differentiable, hence continuous function, defined over a closed interval, there's something called the extreme value theorem that would end up applying, telling us that an optimized point actually does exist, but we're not really going to discuss that theorem here. But as long as you have a continuous function over a closed interval from Calculus 1, and you tested the endpoints, right? You're going to test the minimum over the interval. You're going to test the maximum over the interval. And then you're also going to test what we call critical points, right? You were back in Calculus 1, I think you would say, where is the derivative equal to 0 or perhaps non-existent, right? In the case of something like the absolute value function over some closed interval, let's say -1 to 1, obviously it's minimized at 0 there, but that happens to be a point where the derivative is non-existent. So you got to keep in mind places where derivatives are non-existent also get included as critical points. But if the function has a derivative everywhere, then you're just looking for places that the derivative is equal to 0 to be your critical points. So the extreme values are going to occur at one of these three locations. And so you just have to check those three locations to find like the absolute min or the absolute max. And why is that useful? Well, it's useful because this interval that the function could have, not necessarily should, but could have extreme values at any of infinitely many points. Right? There are infinitely many points inside of this interval. And through our procedure of testing the endpoints and critical points, we reduce infinitely many, which is something a computer or a human cannot really do, to finitely many, right? Because there's only going to be finitely many locations, unless the function's constant, at which the derivative is equal to 0. So you really get to reduce the number of cases that you have to check from infinitely many to maybe five locations, 5, 6, 10, 17, some finite number of cases that you need to check. We're going to try to do the same thing in multiple dimensions, but let's just go through one example of this Calculus 1 optimization just so that we feel good about it. So we can find the absolute max and absolute min of the function defined over the interval -2 to 2 by x squared minus 2x plus 2 by testing the points -2. Remember, that's just the lower bound on the domain. We test the point 2, that's just the upper bound on the domain. And then we test any points which are critical, meaning that the derivative is equal to 0. We'll get the derivative equal to 0, we're going to compute a derivative, so that's going to give me 2x minus 2 here, and of course if that's equal to 0, I see that 2x is equal to 2, or rather x is equal to 1 is my only possible critical point, and so I'm going to go ahead and check, well, the function value at the critical point. If I plug that into my function here, I just get the value 1 out of it, and then if I plug in the endpoints of my function, right, this f at -2 and f at 2, well, at -2, when you plug that into the function, you get 10, and at 2, you get 2, which means our critical point, which outputted a 1, happens to be the minimum, because it's the smallest of these three numbers that we tested, and the 10 over here happens to be my maximum, because it's the largest of the values that I tested. So that's how it worked back in Calculus 1. And we also had this notion of concavity, and really the concavity came from the second derivative test to tell us if a critical point was a local min or a local max, or sometimes inconclusive test. And that'll actually be relevant in multivariable calculus as well. So let's just recall, if we have a critical point of a function, then you can test the second derivative of the function, and if that second derivative is positive meaning concave up, right, it bends upwards, and of course anything that's bending upwards like this is going to have a minimum at the bottom. If the second derivative is negative, then we are going to be concave down, or in other words, we'll bend downwards. And of course, the point would be a local maximum at the top of a downward pointing curve. And then if the second derivative is equal to 0, we unfortunately have an inconclusive test. But there's going to be an analog in higher dimensions for this test as well. So let's just see what that test looks like in one dimension first. And you recall I'm not changing my function here. This is the same function that we just worked with in our Calculus 1 version. we know that the critical point occurs at 1, and so we're just going to go ahead and calculate the second derivative of f. Well, the first derivative, recall, was 2x minus 2, so the second derivative will just be 2, which of course is always positive, and so this function is always concave up, meaning that the critical point must be a local min. Now, it turns out in our case it was also a global min, but the second derivative test can only go so far. It can tell us the local behavior of the critical point. So we get that it's a local min just for the second derivative test, and of course, when we went through and checked all the cases, we found out it was a global min. So moving up to multiple dimensions, we have this method of Lagrange multipliers, and this is really going to be the primary method we're thinking about today, even though we will study the second derivative test as well. Things get trickier in multiple dimensions. It's not too hard to still work with the idea of critical points. So critical points are the same. Say critical points from derivatives equal to 0 are the same as before. But the big problem in multiple dimensions is that there's no such thing as endpoints to check, right? So in higher dimensions, our domains are no longer intervals, and since they're no longer intervals, they don't have endpoints. They have boundaries, certainly, but they don't have endpoints, right? If we go back to kind of one of the very first topics of the semester, we had something like domains. We discussed domains, which I often use as omega in higher dimensions. In these domains, at least in the one I'm drawing in 2 dimensions here, they were open connected sets. Right? So some open connected set here, and then the boundary of the domain was simply what you would directly label as the boundary, as colloquially you would. It's the edges of this object, and the boundary still has infinitely many points, even in 2 dimensions, right? Even in 2 dimensions, that boundary is a curve embedded in 2 dimensions and still has infinitely many points to check. In higher dimensions, the boundary of a ball in 3 dimensions is a sphere. It's the surface of the ball. In 3 dimensions, certainly there are infinitely many points there to test as well. And in 4 dimensions, it continues, right? There's no way to say that the boundary of a domain, the boundary of the domain you would like to optimize your function on, still has infinitely many points. So there's just too many things to check. There are too many points to check on the boundary. And so we have to get more clever than simply checking the endpoints of the boundary. And that cleverness comes from Lagrange. So he was able to discover what exactly the property that needed to exist on the boundary for functions to be optimized there. And so how does this work? Well, suppose we have this multidimensional function f that we wish to optimize, and let's keep in mind that multidimensional functions for optimization, right? So optimizable functions must have a single output, or one-dimensional output. And that's for the sole reason that you can optimize real numbers. You can say what's the largest number in a set of 5 real numbers. There's a natural ordering to them. You can't do that with vectors, right? If the output or points, if the output were like Rn, R11 or something, you had 11-dimensional outputs. There's no way you can kind of order one 11-dimensional output is better or worse than a different 11-dimensional output. So you're always looking for just a single output in these functions. But suppose we would like to optimize that function f, and suppose we would like to optimize it over a specific region. And the region still has to be closed here, meaning that it consists of a domain along with its boundary. Okay, so we're going to be able to optimize over a closed region, meaning this is a domain along with its boundary. And this is the equivalent of optimizing functions over closed intervals in 1 dimension. We just need to make sure we include the boundary. Now we just figured out that the boundary is the part that gets in the way. Critical points still work, where you look for where the derivative is equal to 0. The boundary is kind of the object we're analyzing in higher dimensions. And how do we analyze a boundary in higher dimensions? Well, we analyze this function. So what we need to do is find a function which is equal to 0 exactly when the inputs are the boundary values, or the boundary of the domain. This function in other optimization courses, this is called the constraint or constraining function. We'll just call it the constraint for now. So that function that's equal to 0 exactly on the inputs of the boundary is called the constraint. And Lagrange multipliers says, hey, if you can identify that function, which you often can, we're going to see in our examples, and that the function is either directly presented to us or very easy to extract, Lagrange multiplier says, hey, if I can identify that function, what am I actually looking for? Well, I'm looking for the gradient of the function I want to optimize to be equal to a scalar multiple of the gradient of the constraint. Okay, so Lagrange multiplier says basically one thing. Lagrange says the function can only be optimized on the boundary when the gradient of optimized function is equal to a scalar multiple of the gradient of the constraining function, or constraint, however you want to call that. And that scalar multiple is the whole reason why it's called a Lagrange multiplier, right? So that lambda that's playing the role to modify the gradients is called the Lagrange multiplier. Now, why should this be true? Well, I've come over to the whiteboard here to try to make this clearer. Let's imagine that we have a mountain range. So some three-dimensional mountain range, and we would like to restrict a region of the mountain range and ask for the min and max values within the region. So within this region, I would like to find the minimum and maximum values of my mountain range. Well, there's a few things I can do. I can find where the derivative, or the slope of the mountain range is equal to 0, and it looks like it's right there. So here slope equals 0, that's regular, that's the regular critical point idea. But we also have this boundary. And suppose I walk along the boundary. Suppose I walk along the boundary. Let's say I'm going in this direction. It doesn't really matter which direction I'm going in, but let's just say I walk along the boundary of my mountain range. And suppose I stick my arm outwards. Suppose this is me walking along the boundary, and I'm going to stick my arm straight out. Perpendicular to boundary. As I'm walking along the boundary, there's going to be a couple specific locations in which my arm, which I am pointing outwards, is pointing exactly in the same direction as the gradient of the mountain itself, right? So if we think about the mountain as having its own gradients, right? The mountain's got gradients always point in the direction of steepest ascent. That's the way you define a gradient. So this mountain has all of these gradients vectors on top of it that are kind of pointing in the direction of steepest ascent all around the mountain. There are going to be some special points where my arm, if I'm pointing my arm perpendicular to the boundary, perpendicular to the path I'm walking, there's going to be a couple points where my arm becomes parallel to the gradient. So what I'll mention here is my arm, which is perpendicular to the boundary, becomes parallel to the gradient of the mountain precisely when I reach the min and max along the boundary. Now this would be a local, it's going to be specifically local mins and maxes along the boundary, but there's only going to be some specific locations where that happens with my arm. In this case, where I'm running my arm perpendicular boundary, those locations are probably about right here maybe, right here probably, right here probably, right? So there would be, in the case I've provided, 1, 2, 3 locations, probably one on the backside as well, where you can't see it on the backside of the mountain, where as I'm walking my arm exactly points parallel to the gradient of the mountain. Now parallel could be in the reverse direction, right? It could be pointing opposite the gradient. It could be pointing downwards instead of upwards, but parallelness for vectors just means the directions are some multiple of each other. And so we're looking for the gradient of the function we want to maximize or minimize. That's the mountain. The gradient of the mountain needs to be some multiple because it agrees in directions of my arm, which my arm is perpendicular to the boundary. It turns out that you have to go through a little bit of work to see this, but if you have this constraining function, the gradient of the constraining function will always point perpendicular to the boundary itself. So it's a little bit of work to figure out why that would be the case, but gradients of constraints always point perpendicular to the boundary. So there's a little explanation in the book if you want to read that explanation about why the gradient of a constraint should always point perpendicular to the boundary. But that's what you discover. If you walk along the boundary, you discover that pointing your arm straight out of the boundary, you'll reach your local mins and maxes specifically when your arm is parallel to the gradient of the mountain itself. This is the sort of thing that I actually would advise you do directly yourself, rather than just watch me draw something. I'd go out, find a hiking trail, stick your arm out, and you'll see when you reach your maximum and or minimum value, your arm will always kind of sweep around and eventually point straight up or straight down the mountain that you're hiking or the hill that you're hiking, etc. Just find a good hill and do that with your arm. You'll see it exactly points in that direction. So that's where these Lagrange multipliers are coming from. It's saying you just need your arm to agree in direction. When you're on the boundary, the direction needs to agree with the gradient of the function itself. And then, of course, we always remember we are still looking for regular critical points. These are the critical points where regular critical points where the derivative is equal to 0. Right, and that's just going to tell you that you're at some local min or local max otherwise. Okay, so that proof there is an explanation of what I attempted to draw. I do have a remark which says any point where the gradient of the function or the gradient of the constraint cease to exist are also going to be critical points. This is just like the absolute value function in Calculus 1. It can be a local minimum, even though the derivative doesn't exist there. We're only going to work with differentiable functions in this class, but just keep that in mind in case you're applying this to non-differentiable functions some other time. So let's go through this example. Let's jump back up and see. So we latch on to what we're actually looking for. When we start an example, we're looking for a constraint function. Right, so a constraint which defines the boundary, and then we're going to take the derivative or the gradient of the constraint and set it equal with a multiplier to the gradient of the function we want to optimize, and then we're also just going to look for standard critical points of the function we're trying to optimize. And so when we apply that to this example, we start with the function we would like to optimize. Here that is f of x and y equals x plus y, so that's just going to be a plane. And then we want to find the absolute min and the absolute max of this function over the closed unit disk, which I've defined here. So here's the entire set, which defines the closed unit disk. But of course, we can identify here is the function, which will give us the constraint. And the constraint is only satisfied on the boundary, not on the entire space. Right now, it's an inequality with a less than or equal sign. But of course, the boundary of an inequality is simply that equal sign there. So the constraint, which satisfies the boundary, will just be replacing an inequality with an equality, or in other words, our function g, which will be equal to 0 on the boundary, is just going to be, well, this function, because that function has to be equal to 0 on the boundary, or in other words, g is x squared plus y squared minus 1. So from that point onwards, we know that our function is x plus y, and g, the constraint, is x squared plus y squared minus 1. And so we can just take some gradients, and if the function was x plus y, the partial derivative in x is 1, partial derivative in y is 1, and then when we take the derivative of g, we get 2x as the partial x derivative and 2y as the partial y derivative. So Lagrange multipliers is telling us that this gradient needs to be a multiple of this gradient for everything to work out. So that's what I've written here, is that the function we care about gradient has to be a multiple of the gradient of the constraining function. Now, this by itself, this is a common mistake I always see students make with Lagrange multipliers, is this is a system of 2 equations with 3 unknowns. Right, my unknowns in this case are x, y, but also lambda. So there's 3 unknowns there, and I only have a system of 2 equations. I have to find a third equation that needs to be satisfied, and g comes along to the rescue, or the boundary equation, boundary constraint equation, whatever you want to call it. Constraint equation serves as the third equation in the system to guarantee solutions. Okay, so once we have the boundary or the constraint equation included, it'll make our life a lot easier to find solutions. So I'm going to take these 2 equations and my boundary equation, and I'm just going to group them together into one giant system of equations. And once I have my giant system of equations, I interpret it truly as a system of 1, 2, 3 equations, which I've drawn here. And now I'm simply going to solve the system for x star and y star. These are going to be my critical points. I mean, sometimes in the process you happen to solve for lambda as well, but lambda doesn't get used in the actual critical points. It just gets used to help you solve the system of equations. What I can do in this case, if I'm going to solve for x star or y star, notice I'll solve each of those first two equations and see that x star is 1 over 2 lambda and y star is 1 over 2 lambda. Or in other words, since they're, 1 over 2 lambda is the same thing as 1 over 2 lambda, we find out that x star is equal to y star. Or if I use this bottom equation and then plug in that x star is equal to y star, we find out that 2x star squared is equal to 1, or in other words, x star is equal to plus or minus 1 over root 2. The moment I know x star is equal to plus or minus 1 over root 2, you find out y star is also equal to plus or minus 1 over root 2. And so we end up with exactly two critical points on the boundary. And those two critical points are when I've chosen the positive half of these plus minuses, which will give me 1 over root 2, 1 over root 2, and when I've chosen the negative half of the plus minus, so negative 1 over root 2, negative 1 over root 2. So these are critical points on the boundary. Big question, do I have any critical points on the interior of the boundary, right? So this is no longer a Lagrange multipliers problem, but simply a question of, is the gradient of my function ever equal to 0? Gradient of the function is never equal to 0. And so we don't have any regular critical points satisfying the derivative equal to 0. So no possible critical points on the interior, meaning these two boundary points, which I've already found, are the only two possibilities for absolute max and absolute mins. If I plug those in, if I plug in 1 over root 2, 1 over root 2, I get root 2, right? Recall my function f of xy was x plus y, so I'm just plugging in 1 over root 2 and 1 over root 2 for x and y. If I do the same thing with the negatives, I'm going to get negative root 2. So it's clear here, that's the bigger number of the two. This is the absolute max. And negative root 2 is the smaller of the two, so that's the absolute min. So there's one example of Lagrange multipliers. We can increase the dimension as high as we want. We'll go up to a 3-dimensional problem. Just the mountain analogy doesn't make as much sense in 3 dimensions, but everything else still does. So we've got a function here from R3 to R defined by f of xyz is x times y times z. And suppose I want to find the absolute min and absolute max of my function over the closed domain, which I've defined here just as a generic domain that I've closed. You can once again basically get for free what is your constraining function. I'll say that again. Constraining function comes for free from the domain. And how do I get it from, well, right now it's defining the entire domain with a less than or equal sign. Instead, I just want the boundary. I'm just going to replace less than or equals with equals. That's going to be my constraining function along the boundary. Or if I want it to be equal to 0, I can subtract 6 to the left-hand side. All right, so then my constraining function is x squared plus 2y squared plus 3z squared minus 6. If I go back to my original function here, x, y, z, I'm going to take a gradient of that function. When I take a gradient of that, partial derivative in the x direction gives me yz, partial derivative in the y direction gives me xz, partial derivative in the z direction gives me xy. And then I need to do the same with my constraining function. Partial derivative in x will give me 2x, partial derivative in y will give me 4y, partial derivative in z will give me 6z. And Lagrange multipliers always says this gradient needs to be a multiple of this gradient. In other words, what I've written here, that the gradient of f is a multiple of the gradient of g. And we see once again, this is a system of 3 equations with 4 unknowns. 4 unknowns, we have an x, a y, and a z, as well as a lambda that are all unknowns. How do I find a 4th equation? Well, the constraining equation itself. Constraining equation itself is the 4th equation here. So once the constraining equation is the 4th equation, there you go. I've written them all in one giant system of equations. Or if I split up the vectors as one giant system of equations, I need to solve this, solve for x star, y star, z star. Lots of different ways to do this. Unfortunately, this is not an easy problem to go through because there are so many solutions, but probably the easiest way to solve this is just directly by substitution. So I'm going to substitute different variables in for each other. I'm going to take this first equation and I'm going to solve it for lambda. It's going to tell me lambda is y, z divided by 2x. And since I know that that's lambda now, I'm going to substitute that in for lambda into the second equation. When I substitute that in for lambda into the second equation, we get xz is 2y squared z over x. And then I'm also going to use that version of lambda in the third equation. where we end up with xy is 3y z squared over x. And then in these cases, as long as we assume that z is not equal to 0 or y is not equal to 0, right, because that would kill the left-hand sides here and automatically satisfy the right-hand sides as well, we can simplify both of them to see in the first case that x squared is 2y squared, and in the second case that x squared is 3z squared. So specifically in the case when those two numbers are non-zero, we've learned what x squared is in terms of both y and z, which means that this 2y squared is really playing the role of x squared, and this 3z squared is really playing the role of x squared. And so the bottom equation turns into really 3 copies of x squared is equal to 6, or in other words, if 3 copies of x squared is equal to 6, that makes x plus or minus root 2. Knowing that value of x, let's recall we did have these two values of y and z in terms of x, and so we see that y will be plus or minus 1, and z will be plus or minus 2/3. Now those were only true underneath the assumption that z was non-zero and y was non-zero, so we do have to tackle the cases where those are going to be 0. And in the cases where, well, if we let x be equal to 0, first equation is going to reduce to y times z is 0, so either of them are equal to 0. If y is equal to 0, then the final equation just reduces to 3z squared equals 6, or that z is plus or minus root 2. And that's going to give me a valid critical point of 0, 0, plus or minus root 2. Or in the event that I don't let y be equal to 0, well, we're going to have a 0 for x and a 0 for z, and that's going to reduce me to 2y squared equals 6, or in other words, y will be plus or minus root 3, in which case my critical point is 0 plus or minus root 3, 0. And then we still have other cases, more and more cases. If we let y be equal to 0, the second equation reduces to xz equals 0, so either x is 0 or z is 0. In the event that z is 0, then our final equation reduces to x squared equals 6, in which case we find out that x is plus or minus root 6. And so our point, critical point, is plus or minus root 6, 0, 0. And finally, there's the case when we let z equal 0, which makes the third equation become xy equals 0, meaning that either x could be 0 or y could be 0. And of course, either of those cases has been considered already above. We just did a y equals 0 case and an x equals 0 case. So there's a lot of case checking involved here. I would suggest you read the text a little bit more carefully to make sure you find all of the critical points that are actually in satisfying this system of equations. But I have condensed all of them down here. We've got all possible combinations of plus or minus root 2, plus or minus 1, and plus or minus root 2/3. We also have the case of 0, 0, plus or minus root 2. We have the case of 0, plus or minus root 3, 0. We have the case of plus or minus root 6, 0, 0. These are all boundary critical points. And thankfully, fewer than infinity. There's a lot of them, but it's fewer than infinity, and that's great. So these are all boundary critical points from Lagrange multipliers. And then we're also going to have to find interior critical points. And interior critical points are always easy. These are kind of the basic critical points where the gradient of my function is equal to 0. Well, if I look at the gradient of the function, let's recall what it is. It's yz, xz, and xy. If that's equal to the 0 vector, then I would need each of these 3 equations all to be equal to 0. And we find out that the only case of them being equal to 0 is if any 2 of the 3 variables are 0, in which case the multiplication of our actual function, right, the value of our actual function, value when 2 of 3 inputs are 0 is simply 0. Okay, so we know that if our boundary critical points are either bigger or smaller than 0, then they're going to be the absolute maxes instead of the interior critical point. So we're going to test each of those boundary critical points. And when we do, if we test on the first collection of boundary critical points, we see that the outcome is really plus minus 1 cubed times 2 over root 3, so some positive, some negative cases of 2 over root 3, depending on which plus minus we have chosen out of each of those. And then all of the other cases of boundary critical points give an output of 0, meaning that the true maxes and mins are achieved at these points. They're not necessarily unique, right, because there's multiple cases of these, but the positive give absolute maxes, and the negative give absolute mins, because everything else is 0 that could possibly be a critical point. And so here I try to make everything clear. If I choose an odd number of minus signs from my critical points, then we get the absolute mins, and if we choose an even number of minus signs including 0, 0 is an even number, then we get our absolute max. But they're not unique, right? There's going to be multiple copies of absolute mins and absolute maxes. So that's Lagrange multipliers. We also have a second derivative test. I'm going to make this a little bit faster than the Lagrange multiplier section because I think it makes a little bit more sense intuitively. So our second derivative test in multidimensional cases, we are always going to start out at a critical point, right? This is the starting at a critical point. Because otherwise it's just not going to make sense to really ask questions about local mins or local maxes. We want to know that this serves as a min or a max in the first place. So we're going to start at a critical point, and then we're going to go ahead and compute the Hessian of the function at that critical point, right? The second derivative test should involve the second derivative of my function. And let's recall that a Hessian is actually a matrix. And because the Hessian is a matrix, we're going to look for eigenvalues of a matrix. And in fact, the Hessian matrix at the critical point. So X star critical. So you're finding eigenvalues of the Hessian matrix at the critical point, and the second derivative test says if those eigenvalues are all positive, then the value of the original function is a local min. Eigenvalues all positive, equivalently saying function is concave up everywhere, right? In multiple dimensions, you can be concave up in some directions and concave down in other directions. So importantly, the fact that eigenvalues are all positive, this says the function is concave up everywhere, or in every direction. If the eigenvalues of the Hessian are all negative, then the value of the function at the critical point is a local max, because the eigenvalues being all negative says that the function is concave down in every direction. So of course it makes sense to say a local max because you're concave down in every direction. And the moment that you have both positive and negative eigenvalues, then we actually classify the function, the behavior of the function as something called a saddle point, meaning that there's at least one direction in which the point behaves as a local min and another direction in which it behaves as a local max. I'm going to jump ahead really quick. Towards the end of this section, we have the following graphic, and here provides a really nice example of a saddle point in the middle here. It looks like a Pringles chip, right, my surface, but you can imagine that if I'm traveling in this forwards-backwards direction on the Pringle chip, I behave as a local minimum, but if I'm traveling kind of in the left-right direction away from my critical point right in the middle, I behave as a local maximum. And so you can also see why it's called a saddle point, because the overall shape, not only does it look like a Pringles chip, but it also mimics that of a horse saddle. And then finally, I do want to cover the last bullet point to the second derivative test, which says that if any eigenvalue is equal to 0, the test is going to be inconclusive. So at least the directions in which the Hessian matrix behaves like 0, then you're neither concave up nor concave down necessarily, and you need some more information. So we're just going to do one example of the second derivative test because it goes pretty quickly. What I've got here is a function that's defined by x cubed plus 2xy minus 6x plus 4y squared, and we can go ahead and compute where the gradient of this function is equal to 0. That ends up being the gradient equal to 0, 0, and we're going to solve for x and y. We solve for x and y using substitution. This bottom equation, 2x minus 8y is 0. It's telling me that 2x is 8y, or rather x is 4y. So I'm going to plug x being 4y, so a 4y in for that x. That's going to give me 3 times 4y squared plus 2y minus 6 is 0. Or if I simplify that a little bit, we see that 48y squared plus 2y minus 6 is 0. If I could use the quadratic formula on that equation, we see that y happens to be 1/3, or negative 3/8. And then recalling that x is just 4 copies of y, that tells us that x is going to be 4/3, or negative 3/2. So that means my critical points are 4/3, 1/3, and negative 3/2, negative 3/8. So these are the 2 points we're going to check the second derivative at. So we're going to check the eigenvalues of the Hessian matrix at these points. And when we check the eigenvalues of the Hessian at those points, we need to first compute the Hessian. Well, let's just recall the Hessian is the matrix of second derivatives. So I'm going to take all second derivatives of that function of f. And when I compute all second derivatives, the only term that's going to survive really is going to be the x cubed term. That'll be 6x. Everything else will end up being a constant after I take 2 derivatives. And then we should also remember, thanks to Schwarz's theorem, that the matrix will always be symmetric. So the derivative in x and y will always be the same as the derivative in y then x. Now this is going to be my second derivative. And I just need to evaluate the second derivative at my critical points. Of course, since x is the only non-trivial variable in the second derivative, I'm going to evaluate at 4/3 and -3/2. That gives me 8, 2, 2, -8 when x is 4/3, and it gives me -9, 2, 2, -8 when x is -3/2. Let's recall all the way back from our eigenvalues, eigenvectors section. We had a proposition which told us what the eigenvalues of a 2 by 2 matrix were. It says the eigenvalues of the matrix A, B, C, and D are given by a plus d over 2 plus or minus the square root of a plus d over 2 squared minus the determinant, which is AD minus BC. So I just go ahead and directly plug those in. So if I directly plug in A, B, C, D from my first Hessian, I get the eigenvalues root 68 and negative root 68, which differ in sign, right? The most important part here is we know that which are positive and negative. So the second derivative test is saying since these are positive and negative, that I have a saddle point in the first case. And then in the second case, when we plug in -9, 2, 2, -8, our second Hessian at the second critical point into our formula for eigenvalues, we get -17 plus root 17 over 2, -17 minus root 17 over 2, which you could either use a calculator or just remember that square roots make numbers smaller. So root 17 is smaller than 17, meaning both are negative. And if both are negative, that means concave down. And when you remember concave down, you remember it's a local max. And so there I've concluded that my function at the first critical point is a saddle point, and then the function at the second critical point is a local max. I know the video is going on a little bit long, but I'm going to cover one last thing, and I'm going to try to be as quick as possible. This is the best section to fit it in, and it's something certainly physics courses would expect you to know, or anything like PDEs, if you were taking a course in PDEs. So this is just a new notation. It's an extra operator that describes second derivatives. And this operator is denoted by delta, kind of confusing when we often use delta for change as well. We just have to get used to it and use context clues. Anyway, this operator is called the Laplacian, or the Laplace operator, and all it is the sum of second partial derivatives. And when I mean second partial derivatives, it's just each variable's partial derivative squared. So I'm just going to square the partial derivative on each variable of my function and add all of those terms together. If you like summation notation, I have the summation notation version here as well. So this is called the Laplacian. If you are really quite happy about your Hessian matrix so far, the Laplacian is the trace of the Hessian matrix, or in other words, it's the sum of the entries on the diagonal of the Hessian matrix. So why is it a somewhat important operator? Well, I have this remark here. The Laplacian computes the local curvature of a function. It gives a single number which describes the local curvature of a function. And this is basically in light of the second derivative test, where the eigenvalues of the Hessian were describing concavity upwards in the case when the eigenvalues were positive, and concavity downwards in the case when the eigenvalue was negative. Since the Laplacian is the trace, and if you haven't learned much about trace, the trace is just the sum of all eigenvalues. So I'm adding all eigenvalues together. Laplacian is the trace. It's just going to compute the total curvature, so the total upwards downwardsness of a function. In other words, if the Laplacian of a function is positive, there's a tendency to curve upwards. It doesn't always curve upwards necessarily, but it has a tendency to curve upwards. It's more common to curve up than down. And if the Laplacian is negative, we have a tendency to curve downwards. And if the Laplacian is equal to 0, the function will have equal upward and downward curvature, or I say perfectly equal proportion. Everything's canceling out in every direction in terms of concavity. So I just have examples where I will compute the Laplacian for each of the cases of positive, negative, and 0 curvature. So here's a function, x squared plus y squared minus 1. If I compute the Laplacian of x squared plus y squared minus 1, that's two derivatives in x and two derivatives in y. We're going to add those derivatives together. And when I take two derivatives in x, only the x term is the non-constant term, so I just get the value 2 out of it. And two derivatives in y, only y is the non-constant term, so I get a 2 out of this. We find out the Laplacian is equal to 4, which is positive, and so our function should have a tendency to curve up. If we look at the plot of the function, indeed, it does have a tendency to curve upwards everywhere. A second function here, I have e to the negative x squared plus y squared over 2, and below you can see my computation of the Laplacian. So once again, I take two derivatives in x and add it to two derivatives in y. There's a little bit of chain and product rules that go on here, but you find out the Laplacian is equal to x squared plus y squared minus 2, multiplying e to the negative x squared plus y squared over 2. Let's just evaluate this near the origin. So plug in 0 for x, 0 for y, 0 for x, 0 for y. What do we get? Well, we get a negative 2 e to the 0 power, or negative 2, which is less than 0. So this should have the tendency to curve downward at least near the origin. And if I look at my function, here's the origin, I definitely have a tendency to curve downwards near the origin, right? Eventually, it does get to a point where the concavity changes. You'll notice instead of inflection points in higher dimension, you have inflection curves or inflection surfaces. But concavity eventually does change, but at least near the origin, it's negative, as the Laplacian says. And finally, this example that I kind of already talked about with saddle points, but we can compute the Laplacian on this example, x squared minus y squared. The Laplacian will be partial squared in the x direction, added to partial squared in the y direction. And we're going to end up with, I guess, 2 from the x term and negative 2 from the y term. So the Laplacian of h will just be 0, meaning I have equal positive and negative curvature everywhere. And of course, we already saw that with the saddle point here. You can curve downwards in one direction, but kind of upwards in the orthogonal direction. But even if you grabbed a different point, this one kind of curves very slightly upward in that direction and very slightly downward in this direction, right? So everywhere you have equal tendency to curve upwards and downwards. All right, thanks for sticking with me. I know it was a really long one. Lots of cool things you can do with optimization and concavity in higher dimensions. So that's why I wanted to really cover everything I could. I hope you're starting to appreciate multivariable differential calculus. It really is a beautiful field of study. Anyway, I'll see you in the next one. We're talking about the inverse function theorem and implicit function theorem. See you then. Bye.